So where am I here? Okay. So I would like to finish this part in a short while, because we are done with the the key idea and key result, okay? The rest of the pages is to make simplification for some situations. For example, Dominic asked, what if we have a orthonormal set, okay? Of course, that will be simpler. The big thing will look simpler, okay? So let's see. Okay, so that is exactly the question. Now, that is a big if, okay? Not a must. If our set is orthogonal, or very often approximately orthogonal, meaning we don't want to bother about this. The example I give you, the 1s on the left atom, 1s on the right atom, it means principle S12 will not be 0, but it will be a tiny number, so tiny that let's forget about it, okay? So that is approximately orthogonal, okay? Now, let's make this approximation, thereby Sji will be delta Ji, okay? Then you will see that this sum will pick up just the Aj, and the whole matrix problem becomes something like this, okay? The point is that all the off-diagonal, for example, H12 minus ES12 previously becomes H12 only, because S12 is 0. So all the off-diagonal becomes simpler, just Hji, okay? And all the diagonal also becomes simpler. For example, H33 minus E, that's it, because S33 is 1, okay? So therefore, we can rewrite the whole thing as equation 11. In this form, it is transparent, very obvious that it is an eigenvalue problem of the matrix formed by taking the given Hamiltonian, your basis, keep on doing this Hij. Okay? It is exactly what you learn in mathematics in matrices. Matrix, eigenvector equals eigenvalue times eigenvector. Okay? Although I must stress, the most general form is not this one. The most general form is equation A7. This one. Let's clear it. Okay, it's this one. So we have some simplification if we assume orthonormality. Now, just to remind you how to read this matrix stuff, okay? This is a physicist viewpoint. Remember, actually, we have a basis set of functions behind the scene. When you read this thing, it looks as if those bases disappear. Actually not. Remember, when we say H12, we have a function phi1 star on the left, phi2 on the right, that are the bases. And then the H, the problem in between, and do an integral, okay? So if you sometimes get confused, think about this thing as this, that will help. That's my experience, okay? If that point never bother you, good for you, okay? Now, when you see this, actually it's good to keep in mind that actually there is a basis set hidden here. When we say H23, there is a 2 from the basis function, there's a 3 from the basis set that give rise to this integration, this integral, okay? Again, when you see this column, sometimes you get confused. What does it mean? It actually means this coefficient is going to multiply into this basis function plus this multiply into that will construct back your eigen state. Okay, so this page is just to remind you. Okay, after you are too happy to see our big matrix, fancy stuff, don't forget that we have a basis function to facilitate this transformation from the differential equation, the Schrodinger equation, into a matrix equation. Some of you may think, oh, there is a careless choice, okay? If my basis happens to be the exact eigenstate, true, that is very clever. The matrix will be diagonal already. So it will be E1, E2, E3, and so on, and everything is 0 out there, okay? Then you don't need to do anything more. You just read out the diagonal number. Those are the eigen values. And the column is easy. 1, 0, 0, 0, 0, 1, 0, 0, 0, things like that, okay? But I would also say that it's the easiest choice, because if you know that, you don't even need to start writing it as a matrix. You already solved the problem exactly. Why bother, right? Okay, but that is exactly what people meant by, at the end, solving a Schrodinger problem is to diagonalize a big matrix. Okay, so you can start from here. For those who know a little bit of linear algebra, you start with a matrix. You keep on making transformation, meaning multiply the second row by a number, add to the third row, things like that. You keep on changing that. All these steps, these procedures will not change the eigenvalue, okay? But by doing so, you are introducing more and more zeros on the off-diagonal thing, and hopefully at the end, you have only the diagonal elements, okay? So now, so far we have been handling big matrices, infinite by infinite or million by million. Now let me tell you that in computational physics, it's rather easy to handle million by million matrix. Okay, they're routinely done. Okay, for example, doing material science problems. Nonetheless, if it's too scary for you, don't worry. In your problem set 1, you are asked to analyze in detail 2 by 2 matrices. For example, solve this problem. You will do it, okay? Now, let me announce it very early on in the course. If you know how to do 2 by 2, and if you know how to do 2 by 2 really well, you already know a lot of physics, okay? That will be reflected in 2 questions in problem set 1, okay? So have fun. So all in all, perhaps at the end, you only need to do many 2 by 2 matrices. So you should know how to do that. That is problem set 1. You have to do that unless you give up. So here's a 1-page summary. The next time when you encounter a Schrodinger problem to solve, think about making a choice of basis function. Then in your mind, do the expansion. The next step will be this big matrix equation. Don't waste time to do the derivation, okay? And then at the end, you realize that non-trivial solution means the determinant equals 0. That is an equation for all the allowed energies, okay? that turn the problem into a numerical or computational problem. Okay, so we are done with this first part. Okay, so any question? So far, so good. You understand what I'm saying? Okay. So now we start our journey into making approximations. Okay, to me that is fun. Okay. So the first method that I would like to introduce here, actually, in my opinion, is also a very, perhaps the most powerful method as well, although the purpose is rather limited, okay, but very powerful. The method is called variational method. 變分方法, variational method. It is based on one theorem, but its purpose is very humble. We don't want to solve the whole Schrödinger problem, meaning we don't want to solve for all possible allowed energies. Our humble task is the first point. We want to make an approximation that can guess at the ground state energy of a quantum problem. We are shooting only at the ground state energy. Okay, so get this point before we move on. Okay, don't abuse the the method. Okay, but sometimes we really take it out of this limitation. Okay, but with a good reason, we will see. So very humble. We are aiming at the ground state energy. But I would say it's very powerful because when you move on to other areas of studies, you will see that it is applied to understanding atoms. For those of you may have done some project, you may have heard of Hartree or Hartree-Fock self-consistent field method in doing atoms and molecules. Okay, they are based on this variation method. In solids, in some fancy theory called the BCS theory of superconductivity, that can be formulated as a variational method result. Okay, so even very limited to start with, a very limited task to start with, the applications is impressive. And more importantly, it's very easy to apply. Okay, but a warning, the result can be very nice and it also can be very lousy. Okay, nonetheless, you have not violated anything, even if the result is lousy. Okay, so let me introduce the governing theorem of this idea. It says the following, okay, then I will prove it is the case. So first of all, you have a problem to solve. All right. So again, it could be a problem like infinite well, but with some funny thing here, okay? Or it may be a problem like a harmonic oscillator, but tilted to one side a little bit, not symmetric. All right, so that is an H. And you want to shoot at the ground state or guess at the ground state energy. Okay, so that is the problem in mind. Then the theorem says, make an arbitrary guess. Really a guess, you just try whatever you want on a wave function that you think may be a good guess of the ground state wave function, the form of it. Okay, so this guess obviously requires some sense, some physical sense or quantum sense. So given a problem, you have to guess at what the ground state wave function should look like. Of course, we don't know the exact one. Otherwise, we don't need approximation. Okay, so the theorem says, just guess something arbitrary that you think may be good. Okay, then the theorem goes, you evaluate the energy expectation value. For those who need to be reminded for what it is this expression. Okay, now what is it? You are given a problem, H is given. You make your educated guess of a wave function. Then you can, of course, calculate this integral on top. Okay, phi star h phi. Same thing on the left and the right. All right. Do this integral. If your wave function, your guess, is not normalized, then you need to do this something like SII as well, okay? And then this combination will give you the energy expectation value, all right? If it is normalized, the denominator is 1, thereby you don't need the denominator, you are left with the numerator, okay? But it is a quick big if your guessed wave function is normalized. The theorem says, whatever you guess, you make any educated guess, it is one-sided. Your guessed expectation value will be greater than the ground state energy of the problem. Okay? So the most important point is B2, equation B2. It says, you have a problem in hand H, you just turn on your mind, make some guess of some form that you think, the ground state wave function looks like that. You calculate the left-hand side. What you get, the value here must be greater than, or at best equal to the exact ground state energy. Okay? When will it be equal? Only if you guess it correctly. If you really guess the correct ground state wave function, you will get the equal sign. Most of the time, you are not that lucky. You will get greater than the exact ground state energy. Okay? So this is the content of the theorem. I haven't proved it, but at least do you get the content? Meaning, do you get what it says? 得唔得？行不行？ Okay? Now that's fine. If you get the content, you can apply it. Even you don't know how to prove it, right? That's the point I tried to convey on Tuesday. What I mean with this course, you need an open mind in learning. Okay? We want to apply, right? Apply quantum mechanics. Okay? So now before we apply anything, we better prove it. Okay? But I would like to convey more on the meaning first. Okay? How can we apply such a nice thing? It says any guess, this will be bigger than the actual value. The nice thing is that it is one-sided. Okay? So, you know, if I have a line here that is the target point I want to know, if I just blindly guess at something classically, like playing darts, okay? Sometimes I will get higher, sometimes I will get lower, right? But in quantum mechanics, because there is really a lowest energy, ground state, you can only guess higher you cannot possibly have something that you get lower than that. That is the nice thing about quantum mechanics. And how we can make use of it? We just work harder. Okay? Quantum mechanics is reflect life. Okay, you just work harder, then you will get better result. How does it go? You keep on guessing different trial wave functions, make different guesses. Okay, so here I depict that if you make 4 different guesses, since the theorem says all this expectation value must be higher than the actual ground state value, you just pick the lowest among the 4. Then you have a better guess, a better prediction of the ground state energy. Okay, so do you understand? Do you understand how to play with the theorem? You don't make one guess, you make many guesses of the wave function. You keep on doing it, the lowest one will be the best. Follow me? Do you follow the logic? Okay, rather clever stuff, right? Okay, then before we do anything more, let's prove the theorem. Very simple. I think it's 3 lines, okay? So, remember we have a problem. And formally, we have the Schrödinger equation. So in principle, there exists, although we don't know. We don't know any one of them, okay? But in principle, there exists the energy eigenstate phi n. And for each one, there is an energy eigenvalue En. Formally, they are there. Although we are so ignorant that we don't know any one of them. Okay? Second point, they exist, and this set of exact energy eigenstates form a complete set. All right? So now, it's U that comes in, then you make a guess. You make a guess of the ground state wave function called phi. Since this exact energy eigenstates are complete, you can always think about that your guess is now being expanded in terms of this phi n's. Okay? Now, let's calculate the expectation value with respect to your choice. There is a numerator, that is the denominator. The denominator is this thing. You have made your choice, okay? So therefore, I can plug in the expansion in 2 places, phi star and phi, okay? So phi star will be sum n, an star, phi n star. I'm making use of this expansion. The other phi will be sum m, am, phi m, okay? Integration, integration. Since this thing is Hermitian, this set has some nice properties. They can be made orthogonal, all right? So this will pick up a delta mn, okay? And thereby will kill one sum. The whole thing is sum n, an square, okay? So that is the denominator. How about the numerator? Okay, do the same thing. The only difference is that in the integral, I have a h in between. Remember that although we don't know what they are, we know that they are eigenstates. So h phi m is gm phi m. By the very fact that phi m is an eigenstate with eigenvalue en. We don't know any actual value of that, okay? But mathematically we know, okay? This is a number, a real number, take it out from the integral. Again, we pick up the delta function that will kill one sum, and we have this, okay? So formally, we have the numerator and the denominator. So far, it's exact. Now, the theorem enters. Among all this En, there is one that is the lowest. Okay, that is the ground state energy. The other thing is positive definite. All right. So if I replace every term here, En, by the lowest one, ground state energy, okay, this substitution must give me a smaller thing. Okay, so therefore I have this inequality comes in. Okay, this is the key step. If you follow this step, the theorem comes out immediately. Okay, do you understand this step? Okay, because we're looking for an inequality, a theorem, okay? This is the place where the inequality enters, okay? So now we take this and divide it by the numerator. Do you see you can cancel things out? Okay, so we have the theorem proven, okay? If you want to remember this easily, in Chinese, it is 你乱猜，你只会猜高了. Okay? Pretty good, right? In Cantonese, 底下, okay? 你亂估，你唔會估低咗嘅 ，OK？ 得唔得？你亂估個 wave function， 你只會個 expectation value 只會高過個真嗰個。Okay, pretty nice. It's one-sided. It's very quantum because there exists a lowest one. Okay, and now I would like to introduce a name. Whatever you guess has a fancy name called trial wave function. You see, it's a scientists like this introduce some fancy name to represent some lousy guess, or but sometimes it may be a good thing, but we call it like we are doing something very important, trial wave functions. It's just guess, okay? Get me? So now pretty nice. We have something to start working, right? Remember before this point, every problem you worked on in quantum mechanics are those exactly solvable problems. Infinite well, harmonic oscillator, rotor, hydrogen atom. Okay? That's all the problem you solved. Okay? But now, with this theorem, at least you can start doing any other problem humbly for the ground state energy, okay? But at least you are free. Finally, you are free from solving exactly solvable problems. You know, that is a moment in your life in physics, I would say. So the next thing is why we call this method variational method. Here is the reason. As I already said, we must work very hard in order to make this theorem works for you well, all right? The meaning is that you don't make one guess, you can make many guesses. For example, here I depict that we make 10,000 guesses, 10,000 trial wave functions. Thereby, you will get 10,000 expectation values. Each one of them will be bigger, higher than the actual unknown ground state energy. So I sketch it here. The horizontal axis are unrelated because they are, each one is a trial wave function, okay? Then you dot all the expectation values, okay? There exists an unknown ground state energy. Then you can pick among these 10,000 values, the lowest one, that will be for your 10,000 trial wave functions, the best estimate. Okay? So, do you follow this idea? Keep on trying. The lowest among your results will be the best guess. Okay. Isn't that simple? 得唔得？行不行？ OK 唔 OK？ Okay. Now at this point, you should be able to do all the 5 problems in problem set 1. Everything is there, okay? But if you know the next one, it will be more convenient for you, okay? With this idea, how about that? We try infinite number of trial wave function of a certain form, okay? I'm trying to type in something. Okay. How about trying an infinite number of trial wave functions of a certain functional form? Okay. Now that is really the spirit behind the variational method. The idea is as follows. Instead of keep on trying different things, 1, 2, 3, 4, 5, how about that? We insert a certain parameter or parameters. Can be 2, 3. Simple form will be 1. A parameter into your trial wave function. Then in one shot, you calculate the expectation value, and the answer will be a function of the parameter you inserted into your trial wave function. Then you can draw this thing out as a function of your parameter, and therefore you can look for the lowest value. That will give a best value of your parameter associated with the best value on the energy, this number, okay? So that is the spirit of the variational calculation. We insert some variational parameters into the trial wave function, okay? So that is the idea. Let's see an example, okay? So the problem is an harmonic oscillator. You may say, as that's silly, I know how to solve it exactly. Very good, okay? But let's pretend that we forgot the analytic solution, the ground state energy, okay, which is half h bar omega, okay? If you forget that, well, that's unforgivable. But pretend, let's say, we forgot. Okay, so now the problem is that we have the h. The potential energy function is a parabola, okay? First point is we want to make a reasonable guess of the form of the wave function, okay? Now, obviously, the ground state should be symmetric about x equals 0 due to symmetry consideration. This thing is even, okay? So, and the wave functions should die off away from the center. So 2n should drop, okay? If it is ground state, there should be more probability to find the particle around the place where the potential energy is smaller, so near the center. Okay, so with all this idea, let's make a guess that it is like a cosine, one cosine. Okay, so cosine is one in the middle, die off like this, both sides, okay? But I don't want it to oscillate. So just cosine 0, okay? So cosine lambda x in a range defined by pi over 2 lambda to minus pi over 2 lambda. So I depict it here, and 0 out there, outside. If that doesn't sound anything to you, look at the picture. This is cosine lambda x for one value of lambda, lambda 1, for example, okay? And then when it touches 0, it remains 0. The place here is pi over 2 lambda 1 for this lambda 1, okay? Another one, lambda 2, which is smaller than lambda 1, you will see because lambda is in the denominator in the range, that actually is wider, okay? But that is lower here, all right? So you see one parameter inserted into the child wave function that governs the width. Do you see the point? I'm trying a form, cosine, but I can use one parameter lambda to vary the width of this cosine. It could be a very wide cosine. It can be a very narrow cosine. Okay, do you get my point? Okay, that is what I meant by trying infinite number of child wave function of a certain form. This example, a cosine form, but I am trying different widths. Narrower, wider, everything in between. Okay? So let's carry out. With this form, all we need to do is to calculate this, use this form, calculate the expectation value of h, and divide it by the normalization. Okay? So before doing that, let's think about it like a physicist. If I use a large lambda, that is to say very narrow, okay? So this one, narrower, okay? I'm making use of the fact that the particle will be found more often in this lower potential energy range, okay? So that I'm thinking about expectation value of potential energy part will be lower. That may be good. We are shooting at the ground state energy. However, if this is narrow, the second derivative of this thing will be rather big because the change has to happen in a narrower range. The kinetic energy term is the second derivative, remember? So all this change have to happen within a narrower range, meaning the kinetic energy may not be small, okay? So large lambda, narrow wave function, one is low, the other one may be high. The sum may not be the lowest, okay? Contrary, if I use a small lambda, the cosine will be very wide. But I will sense some bigger potential energy part in the integral. Therefore, potential energy may be high, although the gradual change, the second derivative will be lower. The kinetic energy will be lower. Nonetheless, the sum may not be the lowest. With this understanding, there must be some intermediate optimum with the total energy, the two terms compromise to give you a minimum expectation value. Okay, do you follow me like a physicist? Meng Meng, here you Meng Meng, do you follow this page? This is the picture before doing anything. Okay, so now we think through the problem. Okay, we have thought through the problem. Then we carry out the mathematics. Okay, so we need to do two integrals, the normalization, the denominator, and the numerator. Okay, I did that for you, but I haven't shown you the steps. You better try it out as an exercise. Okay, then use this divided by the denominator. The end result is this expectation value. Okay, now is the point. You see two terms. One should be the kinetic energy term. Okay, you see that goes like lambda square. It means lower lambda, wider cosine, wider range cosine, change gradually will be good for the first term. Okay, that echoes our sense. Do you see? Echoes our physical sense. The second term comes from the potential energy part of this integral. It goes like 1 over lambda square. It says, bigger lambda, this part will be smaller. Bigger lambda means narrower cosine. Of course, it lives near the bottom of the well, where u is small. Okay? However, it is not the total energy. It's only part of the total energy. You have the kinetic energy part. These two parts competes. 競爭㗎. All right? When one is small, one is high, one is, okay? So they have to come together to compromise. There is a best value of lambda that this thing is smallest. Okay? That is the message I'm trying to convey. Okay? But now we have a parameter lambda that we can tune to look for the minimum value. And that is variational calculation. How to do it? d lambda set is 0. Now that is variation comes in. You look for the minimum of the curve. All right? So you do this. At the end, you can solve for the best parameter. But that's not the answer. You have to plug the best parameter back into the expression. Lambda take on the best value, that will be the best guess. Okay? So again, I show you the answer. I haven't filled in the lines. You plug back into the expression. The final answer is this is the best guess of the ground state energy. Okay? You use your calculator to calculate what this thing is. Okay? It is 1.14 times half h bar omega. First of all, this problem, we know the exact result. It is half h bar omega. First of all, it is bigger than that because we have the theorem. The theorem says it should be higher. Secondly, you should appreciate it's only 1.14 times the exact value, only 14% higher. But we don't need to learn raising, lowering operator, Hermite polynomial, all those things, right? We already guessed at 14% accuracy of the ground state energy. You should appreciate that it's not bad. Okay? Of course, for this particular functional form, this is the best we can do. If we make cleverer choices, better child wave function form, we could make this even closer. Okay? In your problem set 1.4, you are doing this. Okay? And you will find out how good it is. Okay? By working out that question in your problem set number 1. All right? So I think I will stop here. You have enough knowledge to work out everything in problem set 1 from this time. Okay? So next time I will show you more example, and then using variational method, but in a particular form of child wave function. Namely, what if the child wave function is a linear combination of several functions? What will be the variational method giving us? It turns out that it will give us a matrix equation of the same form that we discussed in the previous hours, but smaller size. That is to say, this approximation is a truncation of the exact big matrix. Of course, you truncate that is an approximation, and that we can justify the truncation by the variational method, which is an approximation. Okay, so that is the plan for next Tuesday, and then we will start perturbation theory, which again is related to the infinite by infinite exact formalism, the matrix form. Okay, so time out. We are done today. See you next Tuesday.